Hello, my name is Mohammed Al Zarquni, and I am doing this video as part of the teaching and learning assignment number 2 for CI 315 by Professor Ming. So today we have a very interesting topic, and it is Banker's algorithm. So as you may know, there are 3 methods for handling with deadlocks, okay? And that basically is like anything in life. You either try to avoid it from happening, you let it happen, and then you try to fix it, or you just ignore it. Okay. And the same thing happens with deadlocks. Okay. So you either avoid, you either try to recover from it, or just, you try not doing anything and pretending the problem doesn't exist, like in Linux systems. So basically you have a warning that on Linux software that if you're not sure it's properly tested, don't try it or it's going to crash your system. And that's not a very um, good thing to happen. Okay. So basically, Banker's algorithm is a prevention. So it's avoidance. And what it tries to do is it tries to work on mutual exclusion. Okay. It tries to make sure that not all the resources are being used at the same time. So in order to prevent deadlocks, so we have these 4 conditions that we could break either of which to avoid a deadlock. One of them is mutual exclusion. So if we can get rid of that, then we'd have fixed our problem. And that's what Banker's algorithm promises us. So let's move on to the whiteboard here and take a look at how it works. So let's take a look here. Okay. So we have this allocation algorithm. I could have promised that I have written it somewhere. 1 second. Okay. So I'll just move it this way through. We are having some technical difficulties. 1 second. Okay, so now we have these processes that start from P0, P1, and all the way to P4. Okay, and these processes are already running. Okay, and there are 3 types of processes that they're going to take: A, B, or C. Okay. So what happens here is that each process has certain type of instances from each resource. So let's say 0, 1, 0, and then 2, 0, 0. Sorry, they're not really aligned. 3, 0, 2, 2, 1, 1, and 0, 0, 2. So this is an allocation matrix. Okay. It tells you the instances of resources that each process has. Okay. And so basically what Banker's algorithm promises us is to solve it if each process is going to tell me the maximum number of resources it's ever going to need. So we do maximum. Okay. Okay. So you ask the processes, what's your maximum amount of allocated resources that you're ever going to ask for? And you get this matrix. So it's 753, 322, 902, 222, and then 433. And so here you have your already allocated matrix, your maximum matrix, and the available, okay, resources from A, B, and C are 3, 3, 2. So basically, when you take a look into here, you can't just like let all these processes run these available instances. So basically what you need to do is you need to take a look further into what will happen, okay? So basically, we're going to try to, I think, clear that, okay? And we need to have a needs matrix. And so a needs matrix, why? Come on. Okay, a needs matrix is going to have the amount of resources that we need. So the rule is that need equals the maximum amount of like requested resources minus the already allocated resources. Okay, so what is that need matrix going to be like? So basically you subtract from each number. So that will basically be, so if we do process 0 to 4, we'll have a needs matrix that looks kind of like this. Okay, so we subtracted the matrices element by element, and now we have a question. So is this system in a safe state? Okay, so basically what we're going to do is we are going to use the Banker's algorithm to ensure that there is a safe algorithm. Okay, so how do you do that? Okay, it's pretty simple. So remember that the available resources are 3, 3, and 2 of A, B, and C. So you ask yourself, well, can I satisfy the needs of process 0 with my available resources? No. Well, why is that? Because it needs 7 of A, which I don't have. It needs 4 of B and 3 of C. So that there is no way I'm doing process 0 first. And so I'm going to ask myself, well, process 1. Okay. Hi, process 1. Is there any way that you can satisfy my requests? Yes, I actually can, because I already have them. So process 1 is going to go in first. Okay. And then my available needs are going to update. Okay. And I'm going to see how many resources have been allocated to P1 already. So if you take a look into the previous matrix, that is 200. And these will be updated here. So you're going to add them back into your available matrix so that you get 2, 3, 5. Okay, or 5, 3, 2. It doesn't matter. So process 1 has been satisfied. Can we satisfy process 2? Well, no. Can we satisfy process 3? Actually, we can. So basically, after process 3 is satisfied, well, how does process 3 look like? It's 2 on 1. So we're going to add the previous allocation of 2 on 1. So you're going to get 7, 4, and then 3. And then you move on all the way to process 4. Okay, so process 4, can you satisfy my requests? Actually, I can. And then I see that process 4 has only 2 allocated, so I'm just gonna get an update of 7 and then 5 and then 5. Okay, so this is my needs matrix. This is my available resources that I have. Okay, this pen is very horrible. And so the sequence that I did is P1, it's P3, it's P4. Okay, and then I'm gonna go all over again. Can I satisfy the needs of process 0? I can. I have 7. Okay, look here. I have 5 and I have 5, okay, which is perfectly within my need, P0. Okay, and the only process that is left out now is just P2. which I definitely have the needs for. Okay, so that'll be P2. And so what is this that I've written? This is called, this is called the safe um, uh, state. Okay, so safe state sequence. And basically what this allows me to do is it tells me that if I go on P1, P3, P4, P0, and then P2 in order, I will not enter a deadlock. I will successfully avoid. Now, how did I do that? It's because I actually prevented the process of mutual exclusion. Okay.
Okay,
I don't know
here's
how
what I
Google
found
got that.
online.
Thank you.
First, use face recognition to unlock the device.